Hello and welcome back to Introductory Astronomy. Today we're going to finish chapter 17 and we're going to start by introducing the Hertzsprung-Russell diagram, or more commonly referred to as the HR diagram. The HR diagram is a graph shown here on the slide. It is a plot of luminosity on the y-axis versus surface temperature of stars. Now, I want to point out the units used in this graph. For luminosity, we use multiples of solar units. Therefore, number 1, by definition, would correspond to the luminosity of the sun. If you take a look at the sun right here, it is located on the y-axis of 1, and since the sun's surface temperature is 5800 Kelvin, if you take a look at the x-axis, you see it will correspond to a G-type star. So on the x-axis, we have surface temperature in Kelvin, and notice how the temperature is increasing from right to left. And we also have the spectral classification. Oh boy, an F grade kills me from last lecture. That corresponds to the Kelvin temperature. If you take a look at the B-type star Rigel at the top left, you can see that it has a temperature of about 11,000 Kelvin, and that corresponds to a luminosity of more than 10,000 times that of the sun. If we take a look at the star Proxima Centauri at the bottom right, we see that that corresponds to an M-type star of a temperature of about 3200 Kelvin and a luminosity less than 1/10,000th of the sun. Now, HR diagrams are very, very useful because they enable us to sort stars according to their diameters. And how do we do that? If you take a look at this HR plot right here, it is a plot of the 80 closest stars to us. Note that in this HR diagram, there's also diagonal dashed lines, and those dashed lines correspond to constant radius. Also notice that the radius is given in multiples of the radius of the sun. The little circle with the dot in the middle next to the R is the astronomical symbol for the sun. So on the very top, you see 100R that corresponds to the diagonal dashed line. That means 100 times the radius of the sun. The astronomical symbol for the Earth is a circle with a cross in the center. Now, I want to draw your attention to the darkened shaded curve. That curve is called the main sequence. That is where about 90% of the stars are located. The points that are plotted in this HR diagram is for stars lying within 5 parsecs of the sun. At the bottom of the HR diagram lie stars that are very low in luminosity because they're very small. At the bottom end of the main sequence of the dark curve that you see right there, we have the red dwarfs, which are not only small, but they're also cool. Therefore, they have low luminosities. In contrast, the white dwarfs lie in the lower left of the HR diagram and are lower in luminosity than you would expect given their high temperatures. So how is that possible to have such low luminosity with very high temperature? Well, the only way for that to happen is if they are very small. So although some white dwarfs are among the hottest stars known, they are so small, they have very little surface area from which to radiate, and that limits them to low luminosities. This is an HR diagram of the 100 brightest stars. Since they're the brightest stars, they all have higher luminosity than the sun. Now, I want you to also notice that some cool stars lie above the main sequence. So although they're cool, they have low temperatures, they are luminous. This must mean that they are larger and have more surface area than main sequence stars of the same temperature. These stars are called giant stars, and they're roughly 10 to 100 times larger than the sun. Notice how we have the red giant stars that are cooler than the blue giant stars on the upper left, which are hotter. This is an HR plot of about 20,000 stars. This data was taken by the European Hyperco spacecraft, and it represents stars within a few hundred parsecs of the sun. It is one of the most complete HR diagrams ever compiled. And you can see the main sequence and the red giant region. About 90% of stars lie in the main sequence, 9% are red giants, and 1% are white dwarfs. So that was a little summary of the HR diagram. I would like to talk about the cosmic distance scale. Spectroscopic parallax. Now, even though there's the word parallax in the name, it has nothing to do with parallax. But it does use spectroscopy in finding the distance to a star. So how does spectroscopic parallax work? There are 3 steps. In step 1, we start by measuring the star's apparent magnitude and spectral class. So we take a look at the star in the sky and we see how bright it looks to be, the apparent magnitude, not the absolute magnitude. And we figure out the spectral class. Spectral class, remember, has to do with temperature. In step 2, we go to our HR diagram and we use the location of the spectral class to estimate the star's luminosity. And luminosity is how bright the star actually is. Step 3, once we figure out the luminosity, we apply the inverse square law to find the star's distance. Using this method of spectroscopic parallax, we can extend our cosmic distance scale to several thousand parsecs. If you take a look at this diagram here, which represents the cosmic distance scale, from our location of the Earth, if we want to take a look at distances within 1 AU, we need to use radar ranging. If we want to take a look at distances between 1 AU and 200 parsecs, then we can use the idea of stellar parallax, the triangulation method we talked about before. For anything further away than 200 parsecs, but within 10,000 parsecs, we get to use the HR diagram, or what we call the spectroscopic parallax. Now, the spectroscopic parallax calculation can be misleading if the star is not located on the main sequence. If that's the case, then the width of spectral lines is used to define what we call luminosity classes. Now, luminosity classes follow the Roman numerals. Looking from the top of the graph, 1a, 1b, 2, 3, 4, and 5 on the bottom representing the main sequence line. Now, these luminosity classes fall on these locations that are drawn by the black curves on the HR diagram. The width of the absorption lines provide information on the density of a star's atmosphere, as shown in frame B and C. The denser atmosphere of a main sequence K-type star has broader lines, as shown in frame C, than a giant star of the same spectra class, as shown in B. So here's a closer look of luminosity classes. The background color in this HR diagram indicates the temperature of the stars. This classification scheme of luminosity classes allows us to distinguish between the bright supergiants, which have class 1A, such as Rigel, and the regular supergiants, classification 1B, such as Polaris, the North Star. The star Adhara is a bright giant, classification 2. Aldebaran is a giant, classification 3. And Altair is a subgiant, classification 4. Ceres and Vega, just like the Sun, are main sequence star, classification 5. When we give the description of a star, its luminosity class appears after the spectral type. So a good question would be, what is the spectral type for the Sun? Our Sun is a G2 star on the main sequence, so the astronomical classification for our Sun is G25. Polaris, on the other hand, even though it is a G2 star, because it is a supergiant, it falls on the luminosity range of 1b. So the classification for Polaris is G2 1b. So using the luminosity class, we're able to classify and distinguish the giants from the supergiants and the main sequence stars. This table right here shows the variation in stellar properties within a spectra class. For example, an approximate surface temperature of about 4900 Kelvin corresponds to 0.3 solar luminosities, 0.8 solar radii, and a classification of K25, a main sequence star. And an example of that would be Epsilon Eridani. If we take a look at a surface temperature of about 4500 Kelvin, solar luminosity 110 times the luminosity of the Sun, solar radius 21 times the radius of the Sun, the object is K23, a red giant. An example would be Arcturus, and so on and so forth. Which brings me to stellar masses. So we have an idea of figuring out how far away the stars are. Another good question would be, okay, how massive are they? Are they bigger or smaller than our Sun? A lot of the stars, in fact, more than 50% of the stars out in the universe are binaries, which means they come in pairs. They're not isolated stars like our sun. This is very useful because a measurement of their orbital motion allows us to determine the masses of these stars. Visual binaries can be measured directly. A visual binary, just as Kruger 60, which is illustrated here, on the left, you see the orbital diagram for this double star. So Kruger 60 corresponds to 2 stars. On the right, you get to see the actual visual photographs taken in some of the years indicated on the left. So we call this a visual binary because we can actually see these 2 stars separated from each other. We can directly observe them. We can also have what is called a spectroscopic binary. And spectroscopic binaries can be measured using their Doppler shifts. So what we do is we measure the periodic Doppler shift of one star relative to the other as they move in their orbits. Here we have a so-called single line system in which only one spectrum from the brighter component is visible. Reference spectra are shown at top and bottom on the left in this picture. Now an observer would see the spectrum redshifted as the visible component moves away. So at the top right in this case. And it would see it blue shifted as it moves towards the observer at the bottom right. So that's called a spectroscopic binary. There's one other type of binary called the eclipsing binaries, and they can be measured using the changes in luminosity. If the two stars are in a binary system, and they're orbiting in such a way, in our point of view, that they eclipse one another, then we can get additional information on their radii and masses by observing the periodic decrease in starlight intensity as one star passes in front of the other. So if you take a look at frame 1, 3, and 5, both of this, in that case, we receive starlight intensity from both stars. So in the corresponding intensity versus time graph on the bottom, we have maximum intensity. Then on frame 2 and frame 6, we have a cooler star in front of the hotter, bigger star. Therefore, the intensity is going to drop because now we're missing the chunk of starlight coming from the bigger, brighter companion because we have the smaller, cooler star in front of it. And then in frame 4, the cooler companion is now in the part of its orbit that is behind the bigger star, so it's being eclipsed by the bigger star, and now we're receiving all the light from the bigger star but no light from the smaller star, so the intensity drops, but it doesn't drop as much as when the cooler, smaller star is in front, which is why in the intensity versus time graph we have a smaller drop. Now, stellar masses, more than any other stellar property, are very important because it helps us determine a star's position on the main sequence. So this is the HR diagram, and we see the main sequence, the shadowy curve right in the middle. And notice how low mass stars, for example, the 0.2 solar mass, is cool and faint. So they lie at the bottom of the main sequence, Very massive stars, on the other hand, are hot and bright, and they lie at the top of the main sequence. In your textbook, in section 17.3, it goes through it and helps you out on how to measure stellar masses in binary stars. So here's a little summary of how you would approach this. You start by measuring the period and semi-major axis of the orbit in a binary star. Once this is done, you use Kepler's third law to get out the total mass of the stars. So mass 1 and mass 2, the total mass of the binary system. Then you use the Doppler effect to measure the relative speeds of the two stars. Once you have the speed, it will be inversely proportional to the mass of the system. This is going to allow you to calculate the mass of each star. So for more details on this method, look at the more precisely section in your textbook. This pie chart shows the distribution of stellar masses. Notice how the more massive stars are much rarer than the least massive stars. This is the range of masses of stars as determined from very careful measurements in our solar neighborhood. So if we take a look at this pie chart, we see that 41% of all stars are red dwarfs. 28% are dwarfs. 19% are close to the solar mass, so they fall on the main sequence. 8% are 1 to 2 solar masses. And notice how the smallest of all are the giants. Now, mass is correlated with radius and is very, very strongly correlated with luminosity. So if you take a look at frame A, we see the dependence of stellar radius on mass for main sequence stars. These are true measurements that are plotted here. Notice how the radius increases nearly in proportion to the mass over most of the range. And you can see that by the straight line drawn through the data points. On frame B, we have the dependence of main sequence luminosity on mass. The luminosity increases roughly as the fourth power of the mass, and that's indicated by the straight line. Now, a good question would be, why is this happening? And the answer is stellar lifetime. There's a big relationship between mass and the lifetime of the star. And we can describe that in a very simple mathematical expression. Stellar lifetime is proportional to 1 over the stellar mass cubed. So this is telling us that the most massive stars have the shortest lifetimes, which is why we don't see that many of them. And the reason for that is that even though they have a lot of fuel, because they're very massive, they burn it at a very high rate. So if they have a lot of fuel, but they're burning it very quickly, then they end up having a short lifetime. On the other hand, small red dwarfs burn their fuel extremely slowly. This results in lifetimes of trillions of years or more, which is why on that pie chart we get to see a lot more dwarf stars than giant stars. So it all has to do with how quickly they burn their fuel. We just finished chapter 17, and here's a little summary of what we talked about. We talked about parallax one more time. which helps us find the distance to a star. And make sure that you remember that this formula works for only nearby stars. And you have to make sure that for distance you use parsecs, and for parallax you use arcseconds. Apparent magnitude, meaning how bright a star appears to be, is related to its luminosity and its distance by that formula. Absolute magnitude, or luminosity, real brightness of a star, is a measure of the power output of the star. Spectral analysis has led to the defining of 7 spectral classes of stars, starting from hotter to cooler. Oh boy, an F grade kills me. Stellar radii can be calculated if the distance and the luminosity is known. In addition to the main sequence, the average stars, which is about 90%, there are also the red giants, red supergiants, blue giants, blue supergiants, red dwarfs, and white dwarfs. Luminosity class can distinguish a giant star from a main sequence one in the same spectra class, and there's a mathematical relationship for that. 4 pi and sigma are just constants, just numbers. R corresponds to the radius and T corresponds to the temperature. If the spectrum is measured, we can find the luminosity. If we combine that with the apparent brightness, then we're able to find the distance to the star. And I gave you 3 different formulas for calculating the distance. Measurements of binary star systems allow for stellar masses to be measured directly. Mass is well correlated with radius and luminosity, and stellar lifetimes depend on mass. The more the mass, the shorter the lifetime. Study chapter 17.5 through 17.8. You should be able to read the HR diagram and identify stellar properties. You should be able to explain how spectroscopy properties can lead to a distance estimate and how masses of stars can be determined. Until next time.